So, hybrid circuit, a circuit that's not purely in series or purely in parallel. A little bit of both. Okay, and then there are a lot more advanced techniques later on, but we're just going to keep it fairly simple here. So, why is it an hybrid? Well, as you can see, the flow of electron right here go through this resistor and then have a chance to go one way or the other. So that, in a sense, because of this node, will make it parallel, and you can see that those two resistors are indeed in parallel, but this one is in series with both of those. Since it cannot be said that this is purely series or purely parallel, I'm calling it an hybrid circuit. Okay. The way to study hybrid circuits is to draw equivalent circuits to essentially deal with what we have right here, which is in parallel, find an equivalent resistance, and then redraw the circuit, so that then we have a circuit that is in series, and again calculate the equivalent resistance for this. Okay, so let me show you. Equivalent circuit. So the battery doesn't change, it's still a 10-volt battery. The resistor R1 is not going to change either. I'm going to leave it as R1. And instead of the resistor R2 and R3, I'm going to have an equivalent resistor, and I'm going to write it as R2 parallel 3, like this. Okay? Now, those two resistors, as we can see, are in series. So this circuit itself, it's going to become equivalent to the 10-volt battery right here with an equivalent resistance, which would be calculated by using the idea of circuit in series. So let's see what we can do now with numbers in order to calculate all of this. So let's pretend, for the sake of this problem, that the resistor R1 will be an 80 ohm resistor, that R2 is, let's say, a 200 ohm resistor, and that R3 is a 300 ohm resistor. Okay. Again, the battery is 10 volt, and we have all of this. Okay. So, with those values for R1, R2, and R3, let's now calculate this equivalent resistance R2 parallel 3. In the parallel video, we saw different techniques to calculate this, but here we can use the fact that there is an easy video, which would be easy formula for two resistors in parallel, R2 times R3 over R2 plus R3. So in this case, it's going to be equal to 200 times 300 over 200 plus 500. So 60000 over 500. Cancel, cancel. 600 divided by 5. R2 parallel 3 is a 120 ohm resistor, or equivalent to a 120 ohm resistor. So this is like a 120 ohm right here, and R1 is still 80 ohm. Now those two are in series, which means that in order to find the equivalent resistance right here, we just add them up. 80 plus 120 is 200 ohms. Okay? So I'm getting this by drawing equivalent circuits. Now, how do I do the rest of the problem? Well, let's first make sure that we understand what it is again that we are doing when we are solving circuits. okay, when we are studying circuits. We want the current everywhere. So I want I, which is essentially the current leaving the battery, which is the same as this current leaving the battery right here, which is the same as this current leaving the battery right here. So I want I want I1, which is the current going through the first resistor, but it's also the current right here. So I want I1. I want I2, the current through this resistor. I want I3, the current through this resistor. And I also need to figure out the voltage drop by each one of those resistors. So I want the voltage drop by this one, the voltage drop by this one, and the voltage drop by this one. The way we proceed is we're going to start with this equivalent circuit. We're going to calculate I, which is going to be the same as I1. Then once we have I1, we can calculate the voltage drop by this one, which will, with Kirchhoff's voltage law, allows us to calculate the voltage drop by this one. And the voltage drop by this one will be the same voltage drop by this one and this one, since it's equivalent to parallel circuits. And since we know now the voltage for this one and this one, we can calculate the current for those two. Okay, so this is the idea, the plan. Now let's try to see what we can actually do using Ohm's law to calculate all of this. Okay, so we want to find all the currents and all the voltages. Okay. So calculator time. We're going to start with the current right here. So I, it's going to be equal to, according to Ohm's law, the voltage over the resistance. So it's going to be 10 volts divided by 200 ohms. Calculator time. 10 divided by my calculator is not working anymore. Okay, well, good thing I don't need a calculator for this thing. 10 divided by 20 is the same as 10 divided by 200, so is the same as 1 divided by 20. So it's 1 over 2, so it's going to be 0.05 amps or 50 milliamps. This is the current right here. As I said before, it's also I1. So I1 is 50 milliamps, I is 50 milliamps. So 50 milliamps right here, 50 milliamps right here. Based on this, we're going to be able to find VR1. Now, VR1 is equal to R1 times I1, which is 80 ohms times 0.05 amps, okay, which gives us 4 volts. So we now know that the voltage drop by R1 is 4 volts. So right here I'm going to write 4 volts. Now remember Kirchhoff's voltage law. It says that if the battery provides 10 volts of potential difference, all of it is going to be consumed by this. So out of those 10 volts, if 4 volts are consumed by this one, that means that 6 volts is consumed by this. Okay? And since the resistor 2 and resistor 3 are in parallel, the voltage through 2 is equal to the voltage through 3, and they're both equal to 6 volts. So I'm going to have 6 volts right here, and 6 volts right here as well. So now I have 6 volts for this, 6 volts for this, and I want to find I2 and I3. I know that I2 would be VR2 divided by R2. So I2 is equal to VR2 6 volts divided by R2. R2 was 200 ohms, and that's going to give us 30 milliamps. So we're going to have 30 milliamps right here. And Kirchhoff's current law says that the current in I1 is equal to the current in I2 plus the current in I3. Since I have 50 milliamps here, 30 milliamps here, I will have 20 milliamps right here. A working calculator would have been nice, but we do without when we need to. Alright, have a good day.